Good afternoon, everybody. Post lunch, we are beginning with our second session for today. That is the second day of our international conference organized by the Department of Mechanical Engineering of RERFGI, that is Regent Education and Research Foundation Group of Institutions. We are going to start with the keynote speakers taking over this session. We are going to start, that is within a span of 5 minutes. So I hereby and the participants to be ready and make this session a fruitful one. We are going to start with the keynote speech session pretty soon, that is within a span of 5 minutes.
Hello, dear
Yeah.
participants, dear lecturer. In first, thank you for in speaker you are choosing. I am Tuba. I'm sorry, is very exciting. And share and presentation and first just a moment.
Yeah, Tuba, you are actually the first presenter, that is you are going to be the first speaker. So we are going to start the speech from 2:30, that is the Indian Standard Time, 2:30 p.m. onwards, that is 3 minutes, about to 3 minutes. So
Okay.
yeah. So I'll be giving a brief introduction about you, and obviously you'll be heartily welcomed to start your keynote speech, for which we all are so very earnestly waiting. Okay. Yeah, once again, good afternoon to all the participants, that is, the respected professors and the enthusiastic scholars. I welcome you all post-lunch session. It is going to start now. So I welcome you to the session. We are beginning with our second session of keynote speech. The speakers for this session are Dr. Tuba Demirel, Dr. Kiran Kumar Villa, Dr. John Dev Verma, and Mr. Manoj Kumar. And this session will be followed by a technical session that is going to be conducted by Dr. Abhijit Bonik. So our first speaker now is Dr. Tuba Demirel. And before I request Tuba to start her presentation, let me give a brief introduction about her. Dr. Demirel is currently employed as Assistant Professor in Department of Mechanical Engineering of Aegis University. Her main research interest is related to carbon fiber production from artificial and synthetic fibers and testing them in composites. She has published articles in over 10 international journals, 3 book chapters, and participated in about 21 international conferences. Dr. Demirel has previously worked in Cappadocia University as an assistant professor. A genius with a zeal, she is unstoppable, and I will earnestly wish that no obstacle can ever deter her from thus surging ahead. I sincerely thank her to be here to deliver her keynote speech today. Dr. Demirel, I request you now to start with your presentation. Dr. Demirel, please.
Thank you very much. And thank you, dear lecturer, and thank you in India. Now is will and sharing my presentation. Just a moment.
Dr. Demirel, can you please turn on your microphone? It has been switched off, I think, accidentally. Dr. Demirel, I request. Yeah. Thank you.
Now is my PowerPoint is sharing. Paylaşım. Now is my PowerPoint is opened, dear lecturer.
It is there. The screen is visible, but not the topic. The topic is not showing.
Just a moment.
Yok, paylaşım şu an paylaşılıyor.
Yes.
Sorry to interrupt. The PPT is not showing.
I'm Tuba Demiral, an assistant professor Tuba Demiral. My working is Cappadocia University and School of Applied Science Aircraft Avionics Nevşehir, and I'm from Turkey. Then, short of and background story. I studied mechanical engineering at the Fred University in the city of Elazığ, and I completed my master degree at Erciyes University in city of Kayseri. Now, I started to work as assistant professor at Cappadocia University. My area of specialization characterizations, carbon fiber production from artificial and synthetic fibers, and testing and them in composites. My now is presentations contained in first introduction, then experimental studies and experimental results, and I explained its general conclusions. Then I will give the reference.
Dr. Tuba, I'm sorry to interrupt you. Actually, if you are having any PPT, it is actually not showing on the screen. Can you please make the, I mean, there is some problem or something that it is not showing actually.
Not showing activity.
Not showing, and is I apologize. And again, the try. Just a moment.
Şöyle yaptığımız zaman aslında ekranı tamam dediğimiz zaman.
No problem, just take your time.
Now you can see our PowerPoints sharing.
Yeah. Now it is visible. Absolutely perfect.
Yes.
Oldu mu şimdi?
Yes, buradan aldım.
I apologized. Just a moment. As again, I am Tuba Demiral. I from Turkey. I work in the Cappadocia University as assistant professor. My background is I studied mechanical engineering, and I completed master degree in mechanical engineering. My area is carbon fiber productions and composites materials. Then in its content presentations, carbon fiber protections and synthetic fibers productions of carbon fibers. I explained in introductions. Carbon fibers is very important, and today ultralight white materials and containment at least a percent 90 carbon, and these fibers is having that diameter of 5 or 10 micrometers. Carbon fiber has properties similar to steel and has a weight similar to that of plastics. And today is plastics very important, and very important than is carbon fibers. Definition of carbon fiber and historical development in carbon fiber, and looking at this carbon fiber is a polymer and is sometimes known as graphite molecular structure as very strong very material. Carbon fibers that spec is in inventor Thomas Edison's and is apply Thomas Edison's is apply light bulbs. Properties of carbon fibers: high tensile strength and rigid, corrosion resistance, electric conductivity, and is very important properties is fire resistance. Is a fire resistance using that is textile sectors, especially as textile sectors and composite sectors. Carbon fiber is market. Low cost fibers will be reality in next 10 to 12 years, and the market carbon fibers has grown at an annual average rate of about is a percentile in the last 20 years. Is this pictures and looking far and this increasing carbon usings in the industrial is especially carbon polymer composites, and applications is very important. Civil engineering and automotive parts is especially important. Aerospace engineering because is today technology carbon composites materials using the aerospace industries because not flame in heating, not flame in very heating. And these medical applications is today very important because it's very important because these carbon fiber polymer composites not is strong materials and not weight and light is materials than steels, and these other applications. Use of carbon fiber reinforcement polymer in implants and process usings, and this process and these other applications. Is very important structure of carbon fiber. Carbon atom layers, other name graphene sheets, arranged in a regular hexagonal pattern. Depending upon the precursor and manufacturing process, layer planes in the carbon fibers may be either turbostratic and graphitic or hybrid structure. And this, the left, the pictures, turbostratic structure, and the right and picture is graphite structure. And this graphite structure and sheets and one sheet and second sheets is arranged, and this arranged this properly, and this properly. Some image of graphite in the molecular structure of carbon fiber 200 micrometer, and left the sum is hexagonal structure and looking for their participants, and right is pictures. I use I am right. I'm writing in Chim Drive. Yes, in Chim Drive, these 3D boyut 3D arranged is picture. I write the chip drive, and this the sheets, the carbon sheets is arranged. The looking carbon fiber, the cost is very cost because is raw material cost depend on the crude oil, the pricing. The second position is held with about %20 by energy cost. and right picture and pan precursor use in industrial is industrial, and this is energy person and 20 is the important. The raw material is carbon fiber cost. What is carbon fiber research? Productions from to research. The main original material of carbon fibers is pan and viscose rayon and pitch. Is pan oil is made of pan raw material. Viscose rayon is and cellulose the made of. And the pitch is very expensive cost than pan cost. The atomic structure of a carbon fiber is similar to graphite. Commercial precursor for carbon fiber manufacturing is pan, crude oil, rayon, cellulose, pitch, petrol, or coal tar, mesophase pitch, petrol, or coal tar. Is very important average tensile strength, and tensile strength is pan is good than other raw material, and carbon yield is %50'den daha büyük. Nasıl? In 50 15 and bigger than is bigger than is per hike. Objective of the study: the reduce the overall cost of the carbon fiber and activated carbon fiber manufacturing by reducing the processing time required for the thermal stabilization stage. It use of thermal process, accelerator, chemical composition, impregnation with precursor fibers, application of different oxidative thermal stabilization and strates. And this carbon production stage of is looking, and stabilization fiber, carbon fiber, and activate carbon fiber, and three main production. The have is carbon fiber, stabilization or oxidation stage 200 or 300 centigrade degree is heating time and air atmosphere. Then carbon fiber for carbon fiber carbonization stage 100 and 100 or 170 centigrade degree and inert atmosphere. Activation stage is carbon dioxide atmosphere is not need activated carbon fiber, and this is important in for stabilization stage and carbonization stage. Activation stage is optional production carbon for, and this is ayrıntı. Nasıl diyeceğiz? Thermal flow curve of carbon fiber production stage is thermal stabilization, carbonization, and graphization. And this I looking for the detail stabilization or oxidation very important. This is flow card, that the flow card. Then heat treatment of fibers accounts for person, 69 of the total energy consumed during manufacture, with person 48 being consumed during the fiber stabilization, the step, and we give importance to the stabilization phase. And this structure model is original pan fiber. Is right pictures is pan fibers is a white color, and this is the original pan molecular structure. And I write the Chimdra program. This pan. The commercially produced copolymer used the present investigation in comparative composition was percent 90 acrylonitrile and percent 10 vinyl acetate monomers. Carbon fiber predictions is the these pictures dönüşüm. And convert, and this is convert. These stabilizations and kahverengi brown, and these fibers then is carbonization stage of is black fibers, and gravitization is whole black fibers. Carbon fiber production is generally consists of two basic, one optional, and states, and this molecular changing these pictures, and the hydrogenation, the molecular, then ringing, and this ringing is molecular structure, and this birlikte and this with the color changing and oxidations, the whole the ringing molecular structure. These fast carbonization stage and graphitization stage, ringing whole molecular structure. Objective of the study: to reduce overall the carbon fiber and activate carbon fiber manufacturing by reducing the processing time required for the thermal stabilization stage. Buraları geçmiş miydim? Just a moment. Tamam. Introduce new precursor fibers for carbon fiber and activated carbon fiber manufacturing with the easy utilization strategies and application of different oxidative thermal stabilization strategies. And these characterization methods and used is very important for molecular structure belirlemek, for physical and mechanical properties. Analysis is very important: volume density, linear density, fiber thickness, flame test, tensile properties. And I used X-ray diffraction and different scanning, calorimetry, and DCG, footer analysis, and SAM analysis. I used my thesis. X-ray diffraction analysis is very important because determinant atomic arrangement and used measure the size, shape, and internal stress of small crystalline regions. Pan precursor fiber and SEM analysis is right pictures cross-sectional view of a pristine pan multifilaments. Experimental studies, my SGA expanded articles, explain and this explain in first my article a study on a structural characterization of thermal stabilized pan precursor fibers impregnated with ammonium bromide before carbonization stage, and this thermal oxidative stabilization of polyacrylonitrile pan fiber pre-treated with ammonium bromide 5% was performed in the air atmosphere and temperatures between 200 and 250 centigrade for periods of 5 to 75 minutes in a multi-speed approach. The studies demonstrates that ammonium bromide incorporation is highly effective in accelerating nitrile group cyclization by reducing the time required for thermal stability structure is very important, and this ammonium bromide is stabilizations is accelerating, then is pan fiber not flammable after 60 minutes then color has been a black and whole black fiber with this decreasing and required time for the stabilization process of pan fiber. The use of ammonium bromide impregnation is expected to enhance carbon fiber productivity and reduce cost and considerably. This my fiber impregnation and this is ammonium bromide solutions, water solutions is impregnation, then kurutmak, then dry is the air, and stabilizations, multi-step stabilizations is respectively and then whole black fibers. Fiber stabilization is left pictures. I use the footer analysis, and footer analysis has been observed that the fiber burning is influenced by the accelerated cyclization reactions and results in the non-burning behavior after stabilizations. After stabilization, 30 minutes according to other 5 minutes and 15 minutes stabilization is time. It is clear that is right and pictures gradually change from white to reddish brown and blackish and black during thermal pretreatment and air atmosphere with increasing temperature and stabilization time. And this original pan or pristine pan multifibers is the footer view, and the 75 minutes stabilization times, and this the wave this and this reduce carbon hydrogen bonding and increasing carbon nitrogen bonding and carbon bonding is very important. Is ammonium bromide impregnation this experimental. conclusion. Other SGI makale neydi ya? SGL is article, the effects of the ammonium persulfate. In the first use the ammonium bromide, and second article is ammonium persulfate. It's the same multiplicate stabilizations time. Same. And this ammonium persulfate, this resulted enhanced thermal stability, and the same analysis used this experimental XRD, TEGA, and SAM. The experimental results suggest that ammonium persulfate was very effective and efficient in promoting stabilization reactions. The use ammonium persulfate is expected to reduce the overall manufacturing cost of the final carbon fiber, as the same stabilization time. And color change, the ammonium persulfate, for the ammonium persulfate is plant fibers. Converted is 45 minutes the black is completions. Ammonium persulfate is a good than ammonium bromide, because ammonium bromide converted the para materials to 60 minutes, and the 60 minutes where is very important. These experimentals conclusions, the increased volume density values for higher stabilization periods, and the growth of extensive cross-linking. Cross-linking is a ringing molecular structures is important in the stabilized fiber that causes lateral compactions. This fiber and this fiber physical and mechanical properties is 15 ammonium persulfate impregnated, and this volume density will increase. Linear density is increase than reduce, and tensile strength is sürekli and permanently is reducing. And these ammonium persulfate, the microscope görüntü microscope the pictures. Plant fibers alters from the white color through the shades of brown to a blackish and black color in the last phases. Other articles, the impact of is guanine carbonate incorporation. This article we use is the guanine carbonate. The guanine carbonate is 15%. 15% was one is optimum incorporate in the one precursor fibers as accelerate and the same accelerate, and I use analyzes the same other two articles, and characterization technique is very important. XRD carbon for carbon fibers, XRD very important. Footer analysis very important because this and this presented and explain the molecular structure and the same multi-step stabilization, systematic and diagram, and experimental sonuç is very important to this, and compositions of physical properties, 5% ammonium bromide is water solutions, and 15% ammonium persulfate in water solutions, and 15% guiding carbonate is water solutions. Then impregnated raw material or precursor plant fibers is impregnated. This and physical guiding carbonate and ammonium bromide physical properties, this karşılaştırdığımızda and this comparative and 15 guiding carbonate is a 15-minute stabilization time, and ammonium bromide is 60 is stabilization time, is 45 and is 45 minute is guiding carbonate stabilization accelerating is stabilization stage. Accelerating, and compression guiding carbonate and ammonium persulfate, and this the same is concentration and the same, and this 45 minute stabilization time is black guiding carbonate, and ammonium persulfate is 45 and this black, and guiding carbonate and ammonium persulfate the same, converting the color changing. Then linear density and looking for this and 59 and this is a 63 linear density. This is mechanical properties is very good ammonium persulfate. This in XRD of the original path, there are two dominant bands is with spacing is nanometer indexing, and this indexing is 100 and 110 to the hexagonal unit cell. This is compressions is the best chemical water solution is respectively is very important. Guiding carbonate is very good mechanical properties, and ammonium then ammonium persulfate and then ammonium bromide is a good material is guiding carbonate. This is X-ray crystallinity decompression. This ammonium bromide and X-ray crystal and this crystallinity this guiding carbonate and ammonium persulfate. This guiding carbonate is just a moment. And this amorph in red line amorph is blue is blue line is crystallinity. This amorph increased guiding carbonate, then ammonium bromide, and ammonium persulfate is the same, and crystallinity is and the same, like the same. But on these X are the analysis, guanidine carbonate and ammonium persulfate, and then good ammonium bromide. Conclusions, it is known that the thermal stabilization process has a significant effect on the molecular structure in terms of the crystallinity, degree, and crystal size. Impregnation of pan-based multifilament fibers with ammonium bromide accelerates thermal stabilization. This increases cross-linking, aromatization, and oxidation. This pretreatment promises significant reductions in energy consumption. After stabilization, many number rings appear to chain bromine atoms. This is reference is my CG indexes is article has been helped dear Mahbub Rahman, Kemal Şahin Tuncay, and dear my thesis consultor Ismail Karaca. Thank you very much for listening to my presentation, dear lecturer.
Thank you, Dr. Demirel. Thank you so much. A brilliant presentation, without any doubt. Over to the audience. Any question from you? If you have any question, feel free to ask her. She is there to answer your doubts. Audience, please raise your questions if you have any.
Is there no questions? Yes. Dear Andrea, is very again thank you. I'm will happy in this participants in India conference. It's very thank you.
Thank you, and you are always welcomed. And like I did mention that I really thank you from the very core of my heart on behalf of the Department of Mechanical Engineering of RERF GI that you have made time for us to deliver your keynote address with a lovely presentation. And just march ahead, and I wish no obstacle will ever deter you, like I have mentioned. Looks like there is no question from the audience right at this moment. Anybody with a question? No. So once again, thank you, Dr. Tuba Demirel. Lovely presentation, brilliant approach. Thank you once again.
Thank you very much.
We hereby move on to our next keynote speaker. Our next speaker will be Dr. Kiran Kumar Bila. Dr. Bila, please be ready to give your presentation. But before you start, let me give a brief introduction about you. Dr. Kiran Kumar Bila is now the principal of just a second.
Yeah, am I audible to you all?
Just a second. Yeah.
Can I proceed?
Dr. Bila is now the principal of Illusionary Institute of Technology and Management, Guntur, India. His area of research interests are alternate fuels, energy, biofuels, RSM, AI tools, etc. He has published several articles in reputed peer-reviewed journals. Before joining PITM Guntur as a faculty member, he worked in various well-regarded institutes all over India. So Dr. Bila, please take over and begin your keynote speech along with your presentation. Dr. Bila, please.
Thank you, Ms. Bhattacharya. So, am I audible to all?
Yeah, you are audible, sir.
Thank you. Here is my presentation. I am presenting. Can you see my presentation, Ms. Bhattacharya?
Not really, it is not yet visible.
Rahul, can you hear me?
Sir, no, the presentation is not visible. You are audible, you are visible, but the presentation is not there on the screen. Yeah, now it is there. It is visible.
Thank you. Uh, Good afternoon, all. I am Kiran Kumar Billa, and I'm about to share my views on my little research regarding energy source and climate change. So, regarding this one, these are my presentation is segregated in 9 parts: introduction and what I have done in this little span of time as a literature review I have presented, and regarding this waste to energy consumption. So I have tested some practical point of view. So I did some research on research also. I mean, Indian side also. The testing facility is given in chapter number 3, and the waste to energy. In that waste to energy conversion, I have prepared some biodiesels using fish oil and jethro oil. So that is given in chapter 4, and results of those are given in chapter 5, 6, and 7. Finally, I have given some economic points of view. I compared my renewable fuels with the present ongoing conventional fuels, and conclusions in the last. So I give some little bit numbers on this climate changes and what is the crude oil consumption nowadays. I have these numbers are from renewable energy 2018. So crude oil consumption in that year was around 1 billion ton, and the main important point behind this is everybody is doing the same research from so many decades. I mean, from 2 decades, the similar type of research is going on. But in this particular segment, in this short span of time, I have tried to give the solution. I mean, not complete solution, but I mean, what do you call? Just a pushback of this. Planet reserves. So in that, I have utilized some state-of-the-art additives in those conventional biodiesels, so that the technology also has some impact on our issues. So the main thing in using biodiesels is first thing, the strong point in biodiesels are we have a lot of what do you call oxygen in it, and it is both boom and curse also, because oxygen gives you extra boom to the fuel to burn, but at the same time it has an issue with what do you call, it cannot sustain for more time. You cannot keep it, as oxygen is very reactive. It both is a strength and then weakness also. And the very much important aspect as a weakness is operational expenditure and capital expenditure on this. And opportunities as per, if we focus on our waste and crop waste and agricultural waste, as I will discuss in my later parts. So if we locally, if we focus on that one and try to give solution for this, so it will be easy for us. So threats is main thing is we have not we won't have surplus, similar kind of feedstocks we don't have. Locally, we are available different type. As in India is a vast diversified area we have. Depending upon the different climatic conditions and the areas, we have different kinds of crops we have available. But we cannot adapt the same technology to everyone. I mean, every single feedstock to get the biodiesel. So that's an issue. And this is some waste to utilize in countries. So waste generating countries, though India is in a last position, but even though we have to think of the other thing also, we have to think of our neighbors also. So the United States is being the highest waste generating, and you can they are utilizing the waste also. That is another issue. And particularly in my short span of 2 or 3 years of research in that area, I have found vast, fish discards, and we have very lengthy coastal line, 8,118 kilometers of coastal line is there, and in which huge discards are generating annually, and they are gently pushing that when you call valuable feedstock, and we can utilize that one as a valuable feedstock, but we are just pushing that one into what do you call the sea, oceans and rivers also. But if we segregate some part of that one fatty masses like heads and the tail and some skin, we have so much of fats in that, and then usually that fats can be converted into biodiesel, and that biodiesel can be utilized. Of course, we have some issues with the biodiesel. I'll discuss in the last part. So first, we can generate some useful outcome through that waste. And secondly, another area I have found is we have a very huge potential area for what do you call that wasteland. We cannot say wasteland, but it is unproductive land around government sources have some 32 million acres of unproductive lands have been identified. So and not only that, on both we have a huge amount of roads, rural roads and highways and all. So if we use that area of that lands on the both sides of the roads, so there are huge. We have more than 125,000 kilometers of railway tracks are there, and rural roads are there. Road lengths, urban roads, rural roads. There are so many. So if that area is being utilized to cultivate some usable plants, plants. Of course, they are not rain oriented, but there are some areas. Some particular species like Jatropha and Karanja. So those they are perennial plants, and they don't need much of water also. So we can, if with the government of India or government or local governments also, as our state governments also, if you focus on that one, so we can generate useful some feedstocks among them. So another thing, so I already told you. So these biodiesels have some problems with in operation, like heavy this one. What do you call? Fumes, toxic gases come out of that one. So in particularly for that problem, we have generally people used to have additives to compensate that one. So in my perspective, I have gone through some papers, and they have utilized some generated and practically also. So higher alcohols, generally lower alcohols is being used in my literature. What I have found in literature. But in the other hand, if we use higher alcohols in place of lower alcohols, we can have better versions of future fuels. Like I have found a practical one, N-octanol and pentanol. So those higher alcohols I have found which are easy to generate. They can be cultivated, I mean produced using our using in a renewable way also. So we can operate with them also in a economical way also. So those can be, we can say, next generation alcohols. They are in a sentence we can say they will occupy the reinfed position of that lower alcohols. Coming to the we have I told you I have gone through some literature review by using some lower alcohols, and very few heavy handful of operation tapas have been acquired. So using the higher alcohols and particularly this waste biodiesels which are generated using this jatropha and fish oil. So what I found using alcohols and jatropha, it is very viscous in nature, and it is producing so much of NOx. So lowering that NOx is an issue with this jatropha. And using this fish oil, which I have generated from fish waste, what I found is heavy carbon monoxide is coming out. So that is another issue I encountered. So what I found is using another additive to suppress this NOx, and in one experiment, and the other one, if we try to control this CO, excess CO, using another additive, so that will be helpful. I'll come up with my first experiment. I have utilized our National Institute of Technology lab facilities. So there I have utilized this test rig, 4-stroke diesel engine cylinder. So that is the experimental uncertainty. I have used some equations. I'll discuss in the later part. Next, using that, these are the some pictures I have acquired. So this is the first picture is the fish waste I have generated in Calcutta fish market. So from that I have generated some useful fish oil, from fats from out of the fish heads and the tails and other inner parts of the fishes. So another one, this using that seed crusher, I have crushed some what you call jatropha seeds, and I have generated some useful jatropha oil. So these are the some properties of what you call some fatty acid composition. So which you can say it is fish oil is very much unstable. We have heavy in nature because it's viscosity is more. That's why, and long, because of that long fatty, long carbon chains. So next, this is the FTIR report of that jatropha oil. I have the red line is neat jatropha oil, and the other one, the blue one, is the jatropha biodiesel. When compared to all of you know that neat oils can be converted into biodiesels by using transesterification, using that phenomena. So I have converted that jatropha oil to biodiesel and the fish oil to fish oil biodiesel. So this is the other oil I have prepared. So that is fish oil, with methyl esters of fish oil, MEFO. So where next with the I have utilized 5% pentanol in this experiment. Many of the literatures I have found using higher amounts of fish oil, which is giving more NOx, more CO, and giving exacerbated NOx and exacerbated COs also. So in some literature I have found exacerbated NOx, and in some I have found exacerbated CO. So for I tried 30% of fish oil also, fish oil biodiesel also, but I have got not I'm not satisfied with the result they have produced. So that's why I have reduced my extent to 20%, and which I found it is very good. In it is more compatible with diesel like properties. So what I blended is 20% of fish oil if I blended with 5% pentanol, a heavy alcohol, higher alcohol we can say. So that is a better combination, and I have utilized a 25 with 5%, 20 with 10%, 30 fish oil with 5%, and 30 fish oil with 10% pentanol also. So, and these are the properties, and you can see this M20 oil and M20 5% pentanol is almost equal to diesel, very compatible with diesel property. And these are the baseline properties, like what are the fish oil, biodiesel, diesel. So these are the properties of the base oils. And here I have utilized, so without going into the vast statistics that are generated by the engine, this one. So I have utilized response surface methodology to analyze the engine data, what I produced with this numerous amount of combinations I have produced. I have utilized nearly 9 different types of combinations of fuel. So using that huge data that I have produced using here, it is we call analyzer using response surface methodology. So response surface methodology is, here I have utilized 3 input parameters: 20% of fish oil, 25% fish oil, and I have 30% fish oil. There are 3 variables. I have utilized design matrix is 3 into 3 into 3. The second parameter is pentanol, so 0, 5, and 10. And last one is load, no load conditions, and part load conditions at 0.5, and the full load conditions at 1. So these are the combustion aspects, where you can see, if you see that M20 is M20P5 is the 10 is producing higher cylinder pressure, where it is giving without knocking sounds. And so if you see this picture, so here it is pentanol, and in first figure it is pentanol and methyl. In the third, I have tested with pentanol and different combinations of pentanol, and different combinations of fish oil, and I have checked with the energy consumption. So the red marks with the red marks, which you can show that is higher consumption, and this green and the blue are the best ones. Here we can see that is, so at no load conditions, it is absorbing more, consuming more. In higher loads, that is full load conditions, and higher pentanol ratios, we have the blue areas. That means 20% fish oil and 10% pentanol at higher loads are deep in blue color. That means it is giving good results. The model we're using, I told you that I have utilized this response methodology. The model is constructed, you can see, as if all p values are below 0.001. And the other, I have checked with 4 different parameters, output parameters, and those are BSS EC, brake specific fuel, and energy consumption, and second one is carbon CO, next NOx, and lastly HC, hydrocarbon, unburned hydrocarbon. Coming to the second one, carbon monoxide, as the fuel is fully loaded with oxygen, In no load conditions also 20% biodiesel with the higher. Already pentanol means alcohol is blessed with the higher amounts of oxygen. So you can see more oxygen in pentanol in higher proportions. So 20% pentanol with 10% 10% pentanol with 20% higher methyl is giving good results. And here 20% pentanol, in no loads. For intermediate loads also 20% fish oil with 10% pentanol is giving good results. Even in higher loads also 20% methyl with 10% is from 5% pentanol to 10% pentanol, it is giving good results at the higher loads. And in the third one, and last, that is higher carbon, hydrocarbons, unburnt hydrocarbons. So in the third higher alcohol, higher loads at higher loads, so very low proportions of pentanol and moderate 25%, 20 to 25% fish oil is giving good results. So coming to NOx, it producing high NOx at higher amounts of pentanol. So it is giving even though it is giving blue area at 10%, is when compared to other parameters also. On whole, if you give optimization results, this is the optimization blend that I have given by the model. So 20% actual and methyl, 6.5% pentanol at full loads is producing 4.7% higher NOx and 4.1% it is consuming more BSCC. HC is 1% more, and lesser, and 4. It is producing 3.9% when compared to the M20, and it is producing 1.57, little bit energy is consuming 1.5% more. And carbon monoxide, it is giving less when compared to the 13.6% of when compared to diesel. Similarly, it is producing 10.17% lower than conventional diesel, and NOx also 2.48. Even though it is very less, very marginally less, but even though it is lesser than the conventional diesel. Coming to the statistical point of view, in which my model is being validated, I have utilized the mean square error, NSC, national storage coefficients, KG efficiency, and Thiel U2. Using all those parameters, you can see the numbers. So in those numbers also, we can see that the model is consistent. Coming to the next one, I have utilized N-octanol, Jatropha oil with N-octanol. So in this experiment, I have utilized similar 20% Jatropha I have utilized, and 5 to 10% of this one N-octanol I have utilized. So we can see the properties here. Coming to the in second model, these are the three input parameters I have given: N-octanol percentage, DEE percentage, and load. Why I have utilized DEE is in my experiment I have seen that the second number of the fuel is coming low. So that's why I have utilized. I used some very less 2%, 0 to 4% of DE to increase my CTN number of the fuel, so that CTN number is a index of our combustion. That's why I have utilized to give good results. I have utilized that DE. So here I have utilized three inputs: N-octanol 0, 5, 10%, DE 0 to 4%, load 0 and 50% and full load. So in this one also, output parameters are the same. I have checked with carbon monoxide, onboard hydrocarbons, NOx, and finally this break specific energy consumption. So all these are the combustion aspects where you can see that DE 2.5 at 22.5 DE, it is giving good results. These are the graphs I have. You can see. So here also this higher consumptions are you can see at 10% and after, lower consumptions have been at these bluish areas, and this is NOx, where you can see this bluish area will be lower, and these are the NO of this thing, CO. So you can see these blue areas. So this model is also consistent as every in every model you can see the p values are less than 0.001%. So here in this experiment I have found 10% of enolphthonol with 2.5% DE at a full load is producing 4.08% lesser NOx when compared to diesel, and BSCC is 7.9% lesser BSCC, and it is giving 11.72% lesser hydrocarbons, and CO also 13.48% lesser CO when compared to the other. So next, coming to the another important experiment I have done is, as I told you that in using 20% and 5 jethropo oil and 5% to 10% N-naphthalol, the oxygen of the percentage, thickness is getting little bit higher than the conventional. And the second one is a little bit oxygen issues and this thickness issue. So in literature I have found in using some peculiar very state of the art additives like graphene oxides, so it is giving good results. So I tried this nano graphene oxide to experiment with this. So I have it is a good move, as I can say. So here I have utilized three inputs similar like graphene oxide percentage and graphene oxide percentage, enolphthonol percentage, and load. I have used these three input parameters, and similar four parameters of output parameters I have utilized, and the Indian data is fed into the model. The model is also consistent, as you can see this prediction statistical values. So it's the same graphs with the other experiments also. The PSCC, you can see a higher number is lower portions of enolphthonol and graphene oxide. So higher moderate portions of enolphthonol and higher portions of graphene oxide is favorable. You can see using these blues areas. So here also next coming to this CO, bluish areas are favorable, as I said. So higher portions of enolphthonol here, in particular this carbon monoxide, higher portions of enolphthonol and higher portions of graphene oxide is favorable in this response. Coming to onboard hydrocarbons also, higher portions of graphene oxide and the lower portions of enolphthonol is being favored here. So overall, particularly in CO here we can see, so higher portions of graphene oxide and lower portions of enolphthonol in air portions of this is this part is part loads and this is full load. At full load conditions, you can see higher portions of enolphthonol and higher portions of graphene oxide is favorable for CO for response. Finally, the model gave a prediction that 4% of enolphthonol with full, 50% of 50%, not 50%, 50 ppm of nano GO at full load conditions is producing 2.93% consuming less, a little bit 2.95% higher consumption, and it is giving 15.6% lesser CO, and producing 21%, nearly 22% lesser HC, and 3.26% lesser NOx when compared to the conventional diesel. So these are the cost aspects that I have generated using these experiments. So which is producing, which is giving our blend, three blends I have experimented. I mean, the whole I have experimented with 9 into 3, 27 experiment. I mean, model different blends. Among those 27 blends, the model predicted blend is giving 80 rupees per egg. It is giving, I mean, the cost for the producing that mm, blend is 80 rupees, and 77.78 rupees and 79 rupees. So which is very lesser than diesel. As on that day it was 84 rupees diesel. So we can say that it is lesser than the conventional diesel. The only thing, the issue is with the storage, the oxygen content of that. I mean, how much as maybe, what I can say from that experiment is, whenever you prepare that blend, you have to utilize it as quickly as possible. Within 72 hours, I have to complete that. I mean, I have to utilize that one, or the efficiency will go down. So these are the conclusions. So I'll handle my.
Yeah, thank you, sir. Lovely presentation, great efforts, great work. Over to the audience. Any question? Then you can ask. Sir. He is there to answer your doubts, to clarify your questions. So please pose your questions.
Okay, Ms. Bhattacharya.
Audience, if you have any question, you can ask Dr. Villa. He is there to answer.
Okay, thank you. Ms. Bhattacharya, you can give my mic to the
Okay, I
next.
don't think, yeah, anybody has any questions. So thank you,
Yeah.
Dr. Kiran Kumar Villa, once again. And with this, let me move on to our next speaker. Thank you, Dr. Villa.
Thank you, ma'am.
Our next speaker who will be delivering his keynote speech is Dr. John Dev Verma. So I request Dr. Verma to be kindly ready with his presentation, before which I need to give a few words to describe and to introduce him. Dr. John Dev Verma is presently employed as an associate professor in Mechanical Engineering Department of National Institute of Technology, Agartala. His areas of interest are welding, non-traditional machining, laser material processing. He has published his research work in 29 peer-reviewed journals, 8 conferences, and 4 book chapters. So hereby I request Dr. Verma to kindly present his keynote speech. Dr. Verma, please.
Thank you. Thank you for this introduction. First of all, I would like to convey my thanks and gratitude to the organizers who have invited me as the keynote speaker. Now, my topic on which I'm going to speak is on explosive welding. Yes. Is my screen visible?
Yes, sir. Absolutely.
So as all of us, we can see on the screen that the topic is on fabrication of AZ31B and AL5052 composite plates. AZ31B is a magnesium alloy, and aluminum 5052 this has been made through explosive welding technique. So my presentation will be divided like this. First, we'll be going for introduction, then applications of the process, objectives, participant materials, properties of the participant material, experimental conditions, setup, microstructural study, mechanical properties, conclusions. So if we talk about explosive welding, maybe many of us will know the technique. So it's basically a joining technique. All of us we know that there are different welding techniques, and particularly in case of this welding technique, the controlled energy of the detonating chemical explosive is used to create a bond, a metallurgical bond. The materials which are to be joined can be similar or dissimilar. So as we are initiating the explosion, what happens? Because of the detonation, the chemicals energy that is stored in the explosive is converted instantaneously into the kinetic energy, which force the fire plate to impinge obliquely with the base plate to craft a metallurgically strong bond. So whatever we get as a result, that becomes metallurgically very strong. Now, if we look at the principles of this welding technique, so here we can see that a controlled detonation of the explosive is used on the surfaces of the, welding that is to be done. So when the explosion happens, it generates a high kinetic energy, rather a high pressure force, which deform the work plates plastically. So, and as the work plates deforms plastically, it forms a metallurgical bond between these two plates. And the detonation process which occurs, it occurs for a very short period of time. And that's why, since it occurs for a very short period of time, the parent material doesn't get damaged. So that is the beauty about this welding process. Now, certainly there are some parameters, welding parameters, which are very important whenever we look at this welding, because these influences the welding, like standoff distance, what is the velocity of detonation, how are we preparing the surface, what kind of explosive we're using. So all these are very, very important. So as we can see in the figure, that particularly this is where we put the explosive, and this plate is known as the buffer plate, and this is the flyer plate, which welding with the flyer plate and the base plate takes place, and we keep a stand-up distance. Now, if we talk about this base plate, so certainly the base plate is the welding plate, which is kept stationary, as you can see. This is the base plate. So it is always held stationary on an anvil. So, and also we put a backing material which supports the base plate, and it minimizes the distortion during the explosion. And as the backing plate is there, so the distortion that may occur will not occur because of the support. Then there is another plate which is called as flyer plate. So this is called as the flyer plate, as I already mentioned. This flyer plate is going to be welded with the base plate, as I already mentioned. And remember that the flyer plate should always have lower density and tensile strength compared to the base plate. So the material which is having more density will be kept as the base plate, and the material which is having lower density as well as tensile strength compared to the base plate will be kept as a flyer plate. So that is the technique. And either you can keep it parallel or at an angle on the base plate. As you can see in the figure that it is kept at an angle, you can also keep parallel also. Then we call a buffer plate. As we have seen, this is the buffer plate. So buffer plate is situated on the flyer plate, as you can see, and it minimizes the effect of explosion, as I already mentioned. And always we keep a stand-up distance, so distance between the flyer plate and the base plate. And generally, double of thickness of the flyer plate is taken for thin plates and equal to thickness of flyer plates for thick plates. Collision point velocity. The collision point velocity, remember that it has to be less than the sonic velocity. There is another important term which is called as loading ratio, which is nothing but the ratio of mass of explosive to the mass of flare plate. So remember, and if the loading ratio is below the critical value, then the terminal velocity of the flare plate is insufficient and the bonding will not take place. On the other hand, if we keep a large ratio, so certainly what will happen? It will produce molten zones and it will ultimately some damage will occur. As I already mentioned, that explosive is very important. So explosive is placed over the flare plate. And mostly RDX, TNT, Sun 90, PTM, all these can be used in explosive. Then important is velocity of detonation. Velocity of detonation means the rate by which the explosive detonates. So it should be kept as less than the 120% of the sonic velocity. And remember that it is dependent on the type of explosive material as well as density. So whatever velocity detonations we are choosing, it will certainly depend on the explosive material as well as density of the explosive material. So this slide shows the types of explosive welding. Already mentioned, parallel configuration, inclined coefficient, both you can use. As you can see that this is on the left hand side, this is the parallel configuration, and this shows on the right hand side, we show the inclined configuration. Now, where can we use? In ship, chemical process vessels, tube welding and plugging, pipeline welding, transition joints, attaching cooling fins, pressure vessels, heat exchanger tube, very large sheets. So you can see some of the applications. Okay, shipbuilding. If you visit some shipbuilding factory, so this is the explosive building. Explosive welding is very popular. Now, this particular topic, if we talk about the objectives, we have used the technique of the explosive welding technique in order to create a joint in between L5052 and Z31 composite plates, and we have used different loading ratios, 0.7, 0.8, and 0.9, and here particularly discuss about the characterization of the microstructure as well as mechanical properties of the joint at different loading ratios. Now, these are the participant alloys, and here also the dimensions which has been considered are shown. So as you can see in this slide, that dimensions of aluminum alloy is kept as 110 by 80 by 2 mm, and for the base plate it is more than, so it is 110 by 80 by 6. And annealing is done so that it achieves the strength. So the electric knuckle furnace, these are done, and figure E shows the anneal samples. Now these are the mechanical properties of the participant alloys. You can have a look. And this are the chemical compositions of the participant alloys. So as you can see, if we talk about this as a 31B, it contains magnesium, as I have already mentioned. This is a magnesium alloy, 96.5%. It contains aluminum also, and zinc, silicon, manganese, etc. Similarly, these are the aluminum alloys, L5052, and you can see that is 97.21% of aluminum. And these are the experimental conditions, different experimental conditions. Stand-up distance in this particular topic is kept as 4 mm. There are different loading ratios, and parallel configuration has been kept. And the result is whenever we have gone for 0.7, it was perfectly welded. When we have gone for 0.8, it was cracks occurred. Whenever we have gone for 0.9, again we have seen cracks. So this is the experimental setup of the explosive welding process that we have followed. Particularly, you can see that this is the work of Mr. Pravat. He is my PhD student. And this is the detonator working. As I already mentioned, it is capped on the anvil. So this is the anvil, and this is the tank. So that just to, for maintaining safety. This is the detonator that we have used. This is the fill tank which is ready for experiment. And this is the inclined setup of explosive welding. This is the explosive that we have used, and this is the exploder. This is a video of the explosive welding that has been done. So we have to keep a minimum safe distance so that we don't get hurt. So these are the photographic images of the explosively welded plates. As you can see, for 0.7, as I've already mentioned, perfectly welded. Here you can see the cracks has occurred. Here also for 0.9, you can see cracks has occurred. Now, certainly after welding, we have gone for sample preparation in order to carry out the microstructural study. So specimens were cut along the detonation direction and polished with grit waterproof silicone covered papers, 600, 800, 1000, 1200, 1500, 2000, and certainly diamond compound of grades 1 and 1/4 with waste high-fill fluid has been used for the microstructural study. Surface preparation for doing microstructural study. Now, if we look at the morphological analysis of the weldment, that is welded at loading ratio of 0.7. So this shows the SAM image, A, B shows the EDS line spectrum, C shows the elemental mapping, and D shows the EDS line analysis. So here, as you can see that this interface, it appears wavy, right? And wavelength is here we have seen to be 535 micrometer and amplitude of 160 micrometer. And this wave, this is along with a localized skinny diffusion layer that is appearing here. And the wavy interface formation, whatever we can see, this is very much attributed to the kinetic energy that was available, the kinetic energy that was dissipated at the interface. And that kinetic energy dictated the pressure that was developed at the collision front. And that ultimately characterized the nature of the interface as either wavy or straight. So as we are getting wavy, this wavy also is due to the dissipation of the kinetic energy. We may get straight also. That also depends on how much kinetic energy is dissipated. So, and now the interface, if we talk about the EDS line spectrum, okay, figure B, it shows a larger presence of aluminum, as you can see here, this one, and as well as magnesium also. Here, if we talk about the percentages, aluminum, as you can see, it is around 64.7%, magnesium is 34.4%, and with a negligible presence of zinc, manganese, copper, silicon, iron, chromium atoms. And the EDS line spectrum results correlate well with the elemental mapping also that you can see here, this figure. Okay. And if we look at this figure, figure D, the interface, the EDS line investigation across the interface shows steep, here you can see this one, it shows a steep element dispersion lines, which indicates the formation of a locally thin diffusion layers. Okay. So now this is the morphological analysis of the weldment, which is done at the loading ratio of 0.8. So here, as I've already mentioned, that crack occurred, right? And we can see an uneven melted zone and dark spots near the interface. That occurred because there was an increment in the kinetic energy at 0.8, and it dissipated. That's why, as there was an increment, there's a crack formation. It becomes more wavy. The melted zone was uneven, etc. Now here, the increase is attributed to the additional kinetic energy dissipation and the pressure that is developed at the interface. Now here, if we talk about the EDS line, here it indicates that the atomic diffusion, because you do not see a perfectly steep curve here, right? So it's not very much steep. So it means that atomic diffusion took place at interface, and the occurrence of the atomic diffusion in the explosive weld is very much consistent with the prior studies that has been done by different researchers. And the EDS line spectrum, this figure, figure D, it shows that the interface contains 61.6% of aluminium and 37.4% of magnesium, while other elements like zinc, manganese, copper, silicon, ferrous, and chromium, they're also present. Okay. And if after going for a further increase in the loading ratio, that is at 0.9, which augments the fire plate velocity and as well as the dissipation of the kinetic energy, it enlarged the interfacial plastic zone. So what happened? It resulted to enlarge, it resulted in the formation of the interfacial waves. As you can see, it is wavy with a higher wavelength, and the wavelength is found to be 840 micrometer and amplitude to be 166 micrometer. Okay. Now, in contrast to the lower reading ratio, that is when R was kept at 0.7 as well as 0.8, cracks and pores, as you can see here, cracks as well as pores, these are observed for the highest loading ratio, that is at 0.9, and which is near to the interface. And that is happening due to the dissipation of more energy and additional kinetic energy dissipation. That is a reason. And the additional energy that is available after creating undulating surface, as you can observe, it led to crack and pore formation. And here you can see that this flyer plate, that is aluminium 5052, it experienced the dynamic impact. So as you can see in figure C, the EDS analysis showed more atomic diffusion here in the aluminium alloy as well as magnesium alloy than for whatever has been observed at sorry, R 0.7 and 0.8. And this is because at an loading increase in the loading ratio that has taken place, that is at 0.9, it enhanced the kinetic energy dissipation at the interface, leading to an increase in the plastic deformation at the interface, as I've already mentioned earlier. So, and if you look at figure D, the EDS line spectrum, as you can see here, it shows that the major constituents of this either aluminum 5052 and this AZ31B welded interface, these are, I mean, more aluminum is present, that is 60.4%, and magnesium is near about 38.5%, which are coherent also with the XRD result that we have done. So here from these discussions, we can say that the concentration of the weaker parent alloy, here the weaker parent alloy is the aluminum 5052 at the interface, is higher, which led to the degrading of the bonding strength, which is congruent also with the tensile result. Okay. Now let us talk about this micro hardness result. So as you can see that there the disparity of this micro hardness across the interface of these composite plates at a distinct loading ratios, that is 0.7, 0.8, and 0.9 are shown. And increment is hardness, as you can see here, for 0.9, it is more. So it is proportionate to the loading ratio. That means more hardness for more loading ratios, as is consistent with the experimental work that is done by different researchers also earlier. And also the micro hardness value of this aluminum 5052 and Z31B are increased more at the interface, as you can see, for all the attempted loading ratio. Here it is at the interface. These are significantly more in comparison to these values. And so you can say that as significant, this is more because this is caused by a significant plastic deformation which took place occurring at the interface. Now, if we talk about the tensile and shear strengths. So we have seen that the ram tensile and shear strengths are found to be maximum at lower loading ratios, that is 0.7. Because you see, again, hardness is, because there is a relationship in between hardness and tensile strength also. So tensile strength was, shear strength was maximum at lower loading ratio, that is 0.7, and minimum at higher loading ratio, that is 0.9. And we have also observed the presence of crack, hole, as well as uneven melted layer, which resulted in reduced strength for high loading ratio, that is 0.8 and 0.9. Now, actually, mechanical properties are dictated by fracture morphology. And the fracture morphology of the ram tensile sample welded demonstrates, which was done at 0.7, it demonstrates excellent integrity. So with no visible cracks, with no pores on the interface. Okay. And also the fracture that was found, it was homogeneous, no cracks emerged due to the small melted layer generated on the interface. But in contrast, if we talk about higher loading ratios, we have seen apparent ductile rupture characteristics with a massive number of dimples, or you can say grooves or cracks on the interface. And the appearance of these grooves, structure, and the solidified melts of the welded sample agree also with the report of the earlier research. So, and in addition also, the elongation to fracture of this as a 31B and 11505 true welded composite plates, it increased significantly as the loading ratio increased. So these are the points that you can draw as conclusions. So as already mentioned, that the composite plates were fabricated through the explosive welding techniques at varied loading ratios. And these are the conclusions which you can draw. We have seen the wavy interface that was formed in between the aluminum 5052 and SR31 plates, which were welded at all attempted loading ratio, that is 0.7, 0.8, and 0.9. And also, it was noticed that the amplitude and wavelength of the wave interface increased with the loading ratio. It was also noticed that the increase in microhardness is proportional to the loading ratios, as we have seen in the graph. And the microhardness values of aluminum 5052 and SR31B are increased near the interface for all the attempted loading ratios, which were caused by the significant plastic deformation occurring at the interface. At lower loading ratio, thin diffusion layer, as well as unified interface without any kind of cracks, any kind of dimple formation, pores were formed, which resulted in the maximum rep. Since those defects were not there, so ultimately resulted in the maximum ram tensile strength of 167 megapascal and shear strength of 103 megapascal. And we can also conclude that a sound composite joint was achieved at a lower loading ratios. So these are the references, and thank you.
Thank you, Dr. Verma. It has been a lovely presentation. Over to the audience. You are invited for asking questions. Dr. Verma will be there to answer. Questions from the audience, please.
No problem. I mean, if anybody is having any queries also, they can email me. My email address, you can find it in the website of NIT Agartala, www.nita.ac.in. So if anybody wants to get any information on this explosive welding technique, so they can contact.
Okay, so just as sir has mentioned, so any question, if there is no question at the present moment, then feel free to ask your questions at your convenience. Sir has mentioned how you are going to get access to his mail and convey your questions. Sir will be happy to answer. So yeah, with this, I again thank Dr. Jandeep Verma for kindly presenting your keynote speech with a lovely presentation. Thank you once again. And with this, I move on to our next speaker. Speaker is Mr. Be ready with your presentation. You are our next keynote speaker. Before Mr. Manoj Kumar speaks, let me give a about Mr. Manoj Kumar, CSIR Institute of Materials Technology, Bhubaneswar, in Advanced Materials Technology Department. He is a material scientist and his research interests include additive manufacturing, laser material, surface thermal spray coatings, and alloy development. He has published several research articles in SCI journals and his research work in several into for Mr. Kumar, please. You will proceed with your presentation, Mr. Kumar.
Am I audible now? No?
Yes, sir. Now you're audible.
Okay, thank you. Thank you so much. So let me share my presentation. Is it visible, my screen?
Yes, sir. It is visible.
So thank you so much for having me invited for this very prestigious conference you're organizing at your institute. So I'm going to present some of my work, which is related to development of intermetallic and graded composite coating by laser metal processor. So I'm Manoj Kumar from CSIR IMMT Bhubaneswar. I'm working as a scientist over here in the Department of Advanced Metal Technology. So let's come to the point. So as I told in the topic, like we are trying to have coating over nickel plus superalloy. Now let us first understand why superalloys. So before going for understanding the superalloys, let us understand how the materials evolved across the decade. So for the mankind, the first of the satisfactory, high temperature engineering material was stainless steel. But after quite a few decades of use, they realized that it is limited in strength capabilities for the very aggressive use in the components. So now they were looking for some kind of superalloys. So what are those superalloys? So superalloys are basically came up with since the stainless steel was the first satisfactory material, which is iron based alloy. So they first started developing iron based superalloy, and then from iron based superalloy they move up to cobalt based superalloys, and then so on, nickel chromium based superalloys, which includes inconels and mnemonics. So let us understand what are the super thing about these superalloys. So these alloys can be used for higher fraction of their melting points. So this means that these materials are capable of functioning at the elevated temperature, and then also it has a greater oxidation resistance, which is again make it suitable for application at elevated temperature. However, it is realized that the superalloys, especially I'll talk about nickel based superalloy, and specifically again nickel based superalloy Inconel 718. So for this specific alloy, this material again does not survive for a long time without developing any kind of mechanical failure above 650 to 700 degrees Celsius. So this requires a coating, and that coating should help dropping the temperature from the ambient side to its internal component side. So coating is actually integral part of superalloy development in their applications. So let us understand where these coatings and these alloys are used. So typical example I can cite over here is a turbine blades, aerospace they are used in. So in the turbine blades, vanes, discs are the components where the superalloys are used and which are subjected to operating at 1600 degrees Celsius and above. So which metal can survive? So hardly any metallic material without any coating assistance can survive in such situations. So they require thermal barrier coating. We call it TBC. So these TBCs are produced by atmospheric plasma spray or electron beam PVD process with inlet cooling system. So there is a coating and also there is an internal cooling system to cool it down during the process. Now these TBCs are in the process for quite a long time, but still there are some problem associated with this. Like there is a sharp interface. So when you deposit a ceramic coating over the metal, there is an intrinsic difference between the characteristics of metallic substrate and the ceramic top coat. So they do not match together in terms of properties. So there is a sharp interface between the metal and the ceramic coat. So this always leads to development of stresses at the interface and the adherence issues, and that leads to the failure of the coating. So now what can be the solution? So today's era, laser is solution for almost so many of metallurgical problem. I'll talk about details in coming slides. So we call it laser assisted manufacturing. So we can deploy laser to develop coatings of maybe intermetallics or the ceramic matrix composite or metal matrix composite by process called laser surface alloying and laser surface cladding. Now coming to the use of laser, let me introduce basic principle of laser. So laser is light amplification by stimulated emission of radiation. This is how it differs from the normal any visible light what we use. So this is stimulated emission. Now how it works? So basically in the we understand from the physics that the electrons are at the ground states, and when we pump it, and it goes to the very higher stage of the orbital, but these orbitals are short-lived for the electrons. So these electrons come down and at the settle around the metastable state. So when the electrons pumped from E1 to E3, it settles at E2. It requires some kind of stimulation, and when you give some stimulation, the electron will settle from E2 to E1, and that will release a discrete amount of energy, that is a fixed quantity of energy, and that's the laser energy. Okay, so this itself, laser science itself is a big deal. So I just wanted to give you little understanding of laser first. So because we'll be talking laser throughout the presentation today. So these lasers can be applied in various processes and various sectors. So these lasers can be used for cleaning of any metallic surface or any even ceramic surface, and welding of materials, cutting, additive manufacturing. Everybody knows like additive manufacturing, 3D printing, and ablation, drilling, engraving, and many more. And covering the sectors like either medical sector, 3D printing in manufacturing, electronics, aeronautics, jewelry, even like any very precise jewelries. They require laser processing for fine joining or cleaning. They use even the jewelries, for the use of laser, sensors, automobiles, and so forth. So now let us understand how these lasers are serving the metallurgical community. So as a metallurgist or metal scientist or even the mechanical scientists or engineers, what we do in the regular basis with the materials, we do basically drilling, welding, cutting, or some transformation hardening. So these are the range we can do with the laser, and this is basically power density and interaction time. So we can, I'll be focusing mostly on the laser alloying and the cladding portions. Now, before going for using the laser with materials, let us understand how laser interacts with materials. Okay, so when laser falls on the materials, what can happen? So first thing is that some portion of energy will be absorbed by the material and some may not be. So some part of it will be reflected by the radiative emission, or some reflection will take place. And whatever is absorbed, that can help to heat the material, or if the power is sufficient enough, it can melt the material. And if it is even more, it can even remove the material. And by that, we can achieve cutting or drilling. So this is how material interacts with laser. Now, what are the applications, typical applications with this is we can do melting of the surface, or welding up to join two different materials or similar materials. So, and then additive manufacturing, one of the prominent way of additive manufacturing is powder bed fusion method. So there is a powder bed, and over that, if you scan the laser, and that laser will melt the sprayed powder and deposit over there. So by that, you can develop layer by layer deposited any design you wish for. So this is how laser interacts with material. Now, coming to understand, as I discussed in the beginning, that these turbine blades, for example, or any high temperature components require coating. So how the coating is being done till now? So one of the prominent way of coating is thermal spray coating. Now, thermal spray coating is established the society for quite a long time, and it is growing also very significantly. So you can understand some statistics over here. In 2021, it was 8.13 billion US dollar of market, and it is expected to grow up to 14 USD billion by 29. So this is gives annual growth rate of almost 7%. And if you see which areas of the world are prominent partners are utilizing this technique, is mostly the North America, followed by America, and then we come into the Asia Pacific. Okay, understanding about which kind of materials are used for this spraying. So again, the metals and the ceramics are the most used material for the coatings, followed by the intermetallic, which I will be talking about. Okay, and again, there are different process of this thermal spray coating, like cold spray, plasma spray, and electric arc spray, and so on. So this is one snapshot I wanted to present to the audience, how the thermal spray coating market is offering opportunities for the researcher. But at the same time, researchers are exploring other novel, innovative methods for the coating. So, and laser serves the purpose over here. So, understanding the laser now, market for the laser. So we see that laser is growing much faster than the plasma spray coating market. It is almost around, some reports also says about 10% of CAGR. So that laser also growing, but we can notice over that this market share is still almost hardly about $2.5 billion compared to $8 billion of thermal spray coating. Now, interesting part of this is that almost 50% of this share is being used in Asia Pacific zone, and India is a part of it, of course. So there is a great opportunity for the researcher, because although being a very potential and prominent way of modern coating using laser, it is not still developed because of lack of technological development. So there is a huge space for the researcher to come up with innovative coatings and develop the technology for this purpose. So having said all this, let us understand how the laser cladding or the coating by laser works. Okay, and how it is different than the thermal spray coating or plasma spray coating. So the foremost advantage over here is that laser is a point source and a very precise heat source. So when you have a precise heat source, you can use it for doing the precise coating, precise repair or refurbishment of any component. And you can also control the heat input. And when you lower the heat input, you also lower the chances of residual stresses development during the process. And by that, you avoid the failure because of the residual stresses. So this is where the laser stands out in comparison to thermal spray coatings. But still, every process has some limitations. So what are the limitations of laser cladding? So first and the foremost limitation is the equipment cost. It is very costly equipment, and that is why many small players are not able to penetrate into this market and share the revenue. So, and the second limitation after that is the limited material selection. Every material is not laser compatible material. So laser should be absorbed by the material in order to extract the energy, and then only melting or cladding can happen. So all materials are not compatible for laser processing. So that's another big challenge, that we need to develop laser compatible materials for using them for laser cladding or laser coating or 3D printing, additive manufacturing, whatsoever. And another point is, it is a slow process compared to thermal spray coatings. The deposition rate is slower than the other coating processes. So, but still, having all these limitations, the advantages of this cladding wins over, and it's opening a bigger space for the researcher to develop a novel technology and come up with the new ideas. Now, by laser cladding or laser coating, we can have, cladding is basically depositing a new material over the existing component or existing material. And alloying is, you're having a metal surface or the component, you can just selectively melt the surface of the material and supply some foreign element and melt it together. And when it solidifies into a different phase, different material altogether. But still, it happens within the given component. There is no additional deposition over it. So this is the difference between alloying and cladding. So by alloying, we can have intermetallic coatings. And why intermetallic coatings? Because they offer high melting points and also retains its mechanical property at elevated temperature. For the reference, I have given some example for here. After metallic, there are some ceramic and other composites which are capable of high temperature protection for the underlying components. Now, having said all this, I'll present two chunk of work from my experiences. One is from laser surface alloying. So we try to alloy the surface of Inconel 718 with silicon, aluminum, and ZrB2. The idea was to, when we alloy Inconel 718 consists of nickel, iron, chromium. So when we melt with silicon, it will form some nickel silicide, iron silicide, chromium silicides, right? So these nickel silicides and other silicides are intermetallics of high melting points and stable at elevated temperatures. Same thing will happen with aluminum. So if you alloy with aluminum, it will form aluminides, and they are again very good candidates for high temperature protections. Interestingly, we also tried with ZrB2, and it gives very different results. It started forming some borides and some zirconates, complex zirconates. Those are also stable at high temperature, but at the end we realized that silicon registers the best protection, followed by aluminum and then ZrB2. So what we achieved with this is that when we started alloying with varying laser power, we got different depth of alloying. So obviously, when we increase the laser power, the heat input will increase and the depth of alloying will increase. Interestingly, with ZrB2, the increase of depth of alloying was exponential, very high with slight increase of laser power, and that can be attributed to some exothermic reaction taking place during dissociation of ZrB2. Now we got graded microstructure, and now this graded microstructure is graded. So this is alloyed zone where we have developed a very altogether different zone by alloying, where the aluminum or silicon is alloyed, and this is unaffected zone, the substrate zone. So, and you can see the interface. So we have a totally metancitic structure on the alloy zone and the interface joining the alloy zone in the substrate, and substrate remain unaffected. So we have substrate, then interface, then alloy zone. So there is a gradation of composition. We can see over here. So so this is for aluminum. So we can see that in the alloy zone we find the aluminum, but when we go to the substrate there is no aluminum. So we have got the graded composition and also the graded microstructure, and that results in graded properties. So we have got very high hardness on the alloy zone and slightly decreasing across the interface and reaching the hardness of the substrate, which is much lower than the alloy zone. Now we also took interest in understanding the how the phases evolve on the alloy zone. So we realized that change of power is giving very different phase together in some cases, and those phases have different roles in thermal protections and other mechanical properties. So we carried out a very extensive phase analysis, phase evolution during the laser processing for all the three cases when we alloyed with silicon, aluminum, and ZrB2, and we find that almost 30 to 45%, or if you add together, almost 50% of the silicides are formed on the top surface when we alloy with silicon. And similar story goes for aluminum and ZrB2. So we published this work in surface coating technology in 2020, and then we also try to understand how it is useful for protecting the oxidation during the operation. So we subjected the samples for high temperature of 900 degrees Celsius when trying to understand how the oxidation takes place. So we realized that silicon offers the best oxidation resistance. That means it forms a least amount of oxides. So this provides the protection from the high temperature oxidation. And after oxidation, we took out the sample. We tried to understand what are the phases forming, and why silicon alloyed surface is not getting highly oxidized is very evident from its exotic profile, that many of the silicides, we can see nickel silicides, and are still unaffected. They are still stable at 900 degrees Celsius of exposure. And again, for NIL and all these are stable at 900 degrees Celsius. That is why they are able to offer oxidation resistance. They are not getting oxidized. And we again had a macroscopic understanding, and we try to locate the oxides and see the morphology and features. And when we see the cross section, and we trying to see the penetration of oxidation into the alloy zone, we also confirmed that the oxidation is limited to very, very thin layer on the top surface. So this is the summary of approach 1 when we tried to alloy Inconel 7118 with silicon, aluminum, and ZrB2. We find significant improvement of oxidation resistance and improvement of hardness and other tribological properties by alloying. So coming to approach 2. Now in this approach, we did not alloy. We put a different layer altogether by cladding. We call it cladding. So now we attempted a cladding of ceramic. But as I discussed in the beginning, the ceramic and metals are very different in intrinsic property, and they do not go well together. So we have to provide some kind of metal additive with this and then deposit, and then we can slowly grade. So we can have more metal on the first layer of the metallic substrate and slowly increase the composition of oxides, and on the top we can have 100% oxide. So that was the hypothesis, the idea we wanted to work upon. Unfortunately, that did not work because for the same reason that that I'll cover. So let me first tell you the problems. So these are the mathematical equations where the wetting problem occurs. Why wetting doesn't happen? So when there is no wetting between the melted ceramics over the metals, it will not deposit, and even if deposit, it will not have sufficient adherence. So how to overcome that and why this is happening? And second problem is that laser absorption coefficient of materials are different, as I said. So nickel, which is metal, has a very good laser absorption of about 15 to 35%, and whereas zirconium oxide is having only 10 to 20% of laser absorption. So when it doesn't absorb the laser, and if you keep increasing the laser power, it doesn't serve the purpose. So the laser cladding become difficult, and if you go increasing the power, the metal will start evaporating. That is again an issue. So having a optimized zone of laser processing, it is very important. So we have to do lots of trials to come to a narrow window of processing parameters. So we took YSZ powder, which is yttria stabilized zirconia. Essentially, it is ZrO2, and then we took also inconel 700 powder. We mixed them together in the proportion of 5 to 48% of YSZ, and we started depositing over the inconel 718, and we try to understand what happens with the process. So this is how the process looks like. So you take a substrate, you put the mixed powder over here, and then you pass a laser. So this will melt and deposit over here. So after deposition, we took a cross section of each. So we deposited a single track actually for preliminary understanding how the behavior changes with change of oxides and also the laser parameters. So we see that when there is a high metallic component, 95% of inconel 700 powder and only 5 YSZ, there is a very good clad. You can see there is a bulge out of extra deposit of clad over here. You can see even a good clad is achieved at 10 weight % of YSZ. But when we slowly increasing the YSZ, we see that deposition has reduced. Not only that, at 40 weight %, we can see even some kind of crater. So this is not allowing the YSZ to get deposit over the inconel 718. So depositing higher amount of oxides, even mixed with metal, is a very, very critical and difficult task. So that is what we are trying to work upon. So then we try to analyze this. So we find that when we increase the laser power or laser input energy, the deposition will increase, of course. So this is the scan speed. So how fast you are moving the laser beam. If you movement is very fast, that means laser is interacting for lesser time with the materials. So laser input is less, energy input is less. So deposition will happen smaller. So the way we are decreasing the scanning speed, deposition is increasing. At the same time, when we are increasing the YSZ component, I mean the oxide composition in the clad powder, the thickness of the clad is reducing. So this is one of the key point we understood from this experiment. Another key point we could observe here is that when we deposit a significant amount of oxide, every part of all amount of oxide does not go into the clad zone, forming the cermet layer. However, but some of these YSZ powder get deposited on the top surface. They behave like a slag. So when you melt metal and oxide together, you cannot force all the oxides to get mixed with the metals into the clad zone, and some amount of oxides come on the surface and get deposited separately. And this is the problem. We did not expect this. Problem is because this is the cermet zone which has metal and ceramic both, but this is purely ceramic. Now, if you want to have another layer over it, it will be very difficult, because this is again pure ceramic. It will not offer very good adherence to the next layer. So the problem does not lie only with because we are not able to push all the oxides into the cermet layer, but also this extra deposition on the surface is hindering the next layer of deposition over this first layer of clad. So now we wanted to confirm this. So we did elemental mapping. So we can see that in the cermet layer, we have uniformly distributed fine particles of YSZ, and that is what we are looking for. We wanted. But the problem lies over here. We see that on the top of it, there is a 100% YSZ deposition on the top, which will not allow or does not allow the next layer to be deposited above this. So this problem still remains unsolved, and we are still trying multiple ways how to handle this. So if this can go deep inside the clad zone, it will also offer more strength and also offer more thermal barrier effect, and at the same time it will also allow the next layer of deposition, which will make the thicker cladding possible. Now we also wanted to understand how the phase evolves during the processing. So this is the XRD pattern for mixed powder of Inconel YSZ. So we see that there is a monoclinic phase of YSZ is quite prominent in the powder form, but when we do cladding, the monoclinic phases reduces, which is good. So this is another understanding of YSZ, which I can talk in some other occasion maybe. Monoclinic is not a desired phase. We want a tetragonal phase. So why tetragonal? Because tetragonal is a stable phase, and it does not transform upon exposure to the high temperature. So a stable phase is always looked after for better stability of the component. So that is one good thing we achieved, that laser processing also stabilizes the tetragonal phase of YSZ. And this we observed for both the cases where we used 28% of YSZ and 48% of YSZ. Now we try to understand what are the mechanical properties affected by this and how it evolves. So of course, the substrate will have lower hardness because it is purely metallic portion, and when we have a cermet layer, we see increase in hardness. So substrate is having 3.8 GPa, the cermet layer have 6.4 GPa, and YSZ top layer have almost 3 times of it, almost 18 GPa, which is characteristics of a pure YSZ layer. So this again reconfirms the existence of thin continuous layer of YSZ. Now summarizing the approach 2, so we find that it is a very different macrostructure in terms of compared to typical deposition of thermal barrier coating by plasma spray. In the plasma spray, we get a splat-like morphology. Here we get dendritic structure, which is advantageous for retaining the strength at the elevated temperature. And this is possible because the velocity is very different. Velocity of deposition is very different in this case, and there is a absence of melt pool in atmospheric plasma spray. In the plasma spray, melting is partial melting. It's not a complete melting, but in laser processing, we melt it completely. So when complete melt pool solidifies, it has a different solidification behavior compared to solidification of partially melted melt pool, if we call it melt pool. Okay, and we realize that upon resolidification, we find uniformly distributed fine YSZ particles. So that is another looked after properties we achieved, and it also assisted by very rapid cooling in the laser processing. So it cools almost around 10 to the power 5 Kelvin per second, which does not allow the diffused YSZ particle to come out. Majority of YSZ particle cannot come out, and they get entrapped in the rapid cooling. And that is how we achieve the composite coating. And as I discussed, so YSZ coating it develops on the top of the clad zone. When we go for higher composition of YSZ, typically we realize that when we go more than 10% of YSZ deposition, we develop thin layer of YSZ coating at top of the cermet layer, and that is again that can be of we can see as two ways. One is that it does not allow it, or it poses a challenge for next layer of deposition, but at the same time if the YZ layer is continuous throughout the coating, then it can also serve as a separate total 100% ceramic coating, and that can further help in reduction of thermal conductivity. That can be a welcome offer, but it is not very welcome when we look for having multiple layer. So we have to understand. So if you can develop a sufficient thick layer in one layer of deposition, then this is advantageous. But if you look for multiple layer deposition, then this is disadvantageous. So we have to deal with it accordingly. So with this, I would like to summarize approach 2, and I would like to acknowledge my employer CSIR IMMT for funding and providing various research facilities which are housed over here. And I would also like to express my gratitude and thanks to Professor Indranil Manna and Professor Josna Datta Mazumdar for their kind supervision. They supervised me for my BTech, MTech and PhD all throughout in Kharagpur, IIT Kharagpur, and they continuously extending their facilities for my research work. Since we do not have any laser facilities at IMMT, I do take help from their lab and process the samples. I also would like to extend my thanks to my colleagues and collaborators, Dr. Mahedar Devata, Ajit Panigrahi, Mr. Pradut Sen Gupta, and of course my students. And I sincerely thanks organizers for extending their kind invitation to me and giving me opportunity to express or present my work and interact with all of you. So thank you so much. If anybody has questions or queries or suggestions.
Thank you, Mr. Manoj Kumar. Lovely presentation, quite enlightening one for sure. Audience, do you have any questions? If you have questions,
Yes, I have a. Yes, I have a questions.
Yes, please.
I wonder about this and sir, PVD coating, physical vapor deposition coating. I wonder about this comparing PVD coating and thermal spray coating. Which one can be considered as the better coating? Compressions and PVD or thermal spray coating? I wonder this.
Oh, thank you. If you're talking about thermal spray coating, EBPVD is the latest technology in today's time for developing thermal barrier coating, because of fact that they develop a columnar grain. So when we have a columnar grain, so we have a space in the vertical direction. So when we subject this coating for the high temperature application, even if the expansion happen, there is a space for between the grains to accommodate that expansion, and that way it does not allow coating to fail. But in plasma spray, atmospheric plasma spray, it is just flat kind of microstructure of the deposition. So that does not have sufficient room to accommodate the expansion during the process. So EBPVD is a much better process compared to APS. But laser, using the laser, we can also deposit. We are trying to deposit, not yet. I haven't seen any report until now which are having successful deposition of oxides, purely oxides on the metallic substrate. So for time being, EBPVD is the commercial process. Thank you.
And the best is PVD coating, sir. It's PVD coating.
PVD is a coating process for very thin layer of deposition. With PVD, we cannot deposit a thick layer. It is with diffusion based coating, and that is very limited thickness.
Yes, thank you.
Thank you.
Any more questions? Anybody? Well, looks like there is no more question to Mr. Manoj Kumar. Okay. Thank you, thank you, Mr. Manoj Kumar, and thank you, Dr. Tamiral, once again for such a question which is a valid as well as an apt one. And thank you, sir, for answering that so brilliantly. Thank you, sir, once again for your keynote speech and your lovely presentation. And with this, we conclude the session of keynote speeches. And now we are moving on to our final, or rather the penultimate final section, that is the technical session. The technical session will be now conducted by Dr. Abhijit Bonik. So before requesting Dr. Abhijit Bonik to kindly conduct the session, let me just give a brief intro about him. Dr. Abhijit Bonik is working as Assistant Professor in Mechanical Engineering Department at NIT Mizoram. His research interests are material science and manufacturing technology. So over to Dr. Bonik. Please initiate your technical session. Dr. Bonik, please. Dr. Abhijit Bonik? Yes.
So with this, I would like to start the session and like to call for
So, preparing 1, 2, 3, Swarup Koda. So, can you join me in your slide and share your presentation?
Okay, sir. Sir, I am audible?
Yes, you are audible. Yes.
Okay, ma'am. My PPT is visible, ma'am?
No, it is
No,
not yet
no.
visible. Just make sure you have time of 5 minutes. Okay, within the 5 minutes, you complete your presentation.
PPT visible, ma'am?
No, not really. Not yet.
My PPT is visible, sir?
Yes,
Yes, now it is visible. Yes, yes.
Good afternoon to all. I am Swarup Gorang. I am BTech final year student in Mechanical Engineering from Durgapur Institute of Advanced Technology and Management, Durgapur. I am going to present review paper. The topic shown electrical discharge machining and overview. So next slides contents. These are my today's contents. First, introduction, working principles of electro discharge machine medium, then dielectric fluid system of EDM, advantage disadvantage of EDM, then parameters of EDM, literature review, conclusion, future scope, then last one of some reference. So next slide, introduction. In the year 1914, two Russian scientists B.R. Lazarenko and N.I. Lazarenko developed the electro discharge machining medium technique. So it is the thermoelectrical energy and their non-conventional machining process. That means in the machining time there is no direct connection required between tool and workpiece, and it is also called spark erosion machining. EDM machining is several types. So die shrinking EDM, wire EDM, and micro EDM. There are 3 types of EDM. So next slides, working principle of electro discharge machining. In these slides, I have shown the figure number 1, working principles of EDM process. First job is placed here where is mentioned working principle or after working principles. So hello sir, working principle of EDM process. I am visible, sir. Hello.
Your PPT is not visible, and please go to your work what you have done.
Sir,
So
her
show
technical
your work
problems.
and progress.
Yes, sir. Sir, my screen is show, but
Okay, we'll proceed with the next paper ID 129. Uh, Doipan Gupta.
Am I audible, sir?
Yeah, yeah, you are audible.
Oh, sir. So there is a little technical issue on my side. My computer system speaker is broken, so that is why I am again available here through my phone. But I am presenting through my computer, so I think it will be visible to you. So I'm presenting now, sir.
Okay, okay. You can proceed for it.
So is it visible, sir?
Yeah, it is visible, and make sure you have 5 minutes time. Okay, within 5 minutes.
Okay, sir.
Present.
Okay, so the topic of my article is the effect of Brassica nigra, which is mustard seed oil, and Helianthus, which is sunflower seed oil, mixed with water and suspended graphite microparticles as cutting fluid for reducing heat generation and friction in turning operation of EN19 steel using high-speed turning tool. I am Doipan Gupta, a Master of Technology students from the Department of Mechanical Engineering in Dr. Sudhir Chandra Su Institute of Technology and Sports Complex under Maulana Abul Kalam Azad University of Technology. So, as we all know that in case of machining process, material removal process like turning, milling, all these process, there is always a huge amount of heat generation because of the transformation of mechanical energy into thermal energies. Now, there is also a huge amount of frictions are present there, but in case of most of the operations, like in this case, I am working on turning. In turning process, due to the during chip flow, as there is a plastic deformation zone, there creates interlocking. So if we apply cutting fluid during turning operation in order to reduce friction, so turning fluids or cutting fluids, they can